Hi, folks. Lauren, they, them. I work at Netflix on our GraphQL platform team, and I wrote a book on GraphQL. I built a web app for you all, and it's a combination of a few of my favorite things. It's got GraphQL, federation, real-time data, AI, and something called durable execution. And I'd like to share this app with you to show how well these things can all fit together. And I'll start out with demo of the app, and then go through some different possible architectures we could use to implement it, and then look at how it's implemented in my app with the federated subscriptions, and then looking at the durable function, and then looking at the LLM code. So starting out with the app, we've got this group chat. And I'm in the group chat, and I have this question about GraphQL. On the client, how to differentiate between fields that are null because there was an error and fields that are intentionally null. And then GPT-4o mini gives a response, and it says, oh, you can add some fields or have some error codes and some other options. And my teammate, Juliana, doesn't really like any of those options. So she asks a question, and then another teammate, Mark, chimes in. And I don't know what happened to the tab on the left, but we can look at the tab on the right. And see that the AI responds to both of the questions in the same message. Let's go back to null and errors. There we go. So GPT says, CCN RFC is still under discussion, and it's not yet an Apollo client. But when it is implemented, it'll be helpful. So it's responding to both of these. And yeah, I'm also looking forward to CCN helping to solve that problem. So this is the app, and there's different ways we could build this. The most basic, simple option is we have the client open a WebSocket to a single GraphQL server in a single host, do a subscription, and the server keeps track of everything in memory, both the pub sub and the state, and talking to OpenAI. But our company is growing really successfully, and we need to split up this between multiple teams because they want to use Rust, and we're a Go shop. And we want to operate independently. So we have microservices. We separate this out into a federated graph. We've got a messages subgraph or service and a user service. And the router opens up. Well, let's say when the client does a subscription to the router, says like I need all the new messages that come to this group. The router will first dedupe if there's multiple clients doing the same subscription for the same group. Dedupe, and then open a single WebSocket and do a single subscription to the messages subgraph, which will send new message events over the WebSocket to the router, which will send it to all the clients who subscribe to it via a HTTP multi-part response, which is a nice thing that Apollo router supports, and is sort of more widely supported than WebSockets. So it's nice that we can have multiple teams working on the same supergraph at this point. But we are getting a lot of traffic to our messages subgraph, and we need to scale it beyond a single process. So when we had a single process, it was easy to do the subscriptions. But when we have multiple processes, let's say the router opens up a WebSocket to host A in the messages cluster, and there's a create mutation that gets routed to host B. How does host B? It needs to tell host A somehow that there's a new message, so it can set it on the WebSocket to get it back to the client. So a common way to do this is with some kind of pub sub or event mechanism like Redis or Kafka. And when the host A gets the subscription, it'll subscribe to this group in Redis, and all of the hosts will publish to Redis whenever there's a new message. then the host A will receive it and send it out via the WebSocket. But it would be nice to be able to simplify this because we don't want to maintain Redis. We don't want to have another possible point of failure or dependency. So we can simplify this by using webhooks instead of WebSockets. So another nice thing that Apollo Router supports is HTTP callbacks as a way to provide subscription events instead of having a persistent, like a open WebSocket connection. So when the router gets a subscription, it generates a callback URL, gives it to the messages subgraph saying, hey, whenever you have a new message event, send a request to this URL, which is my URL. And now all that host A needs to do is get that URL to the others, which is much easier to the other hosts, which is much easier to do than doing all of the pub sub stuff. Like you can save the callback URL in the database alongside the group record. All right, so we simplified. We don't need Redis anymore, but we need to make this more reliable. And there are a number of problems with the reliability in the current system because messages subgraph hosts still store things in memory, so like the group state. And it would be sad if something happened to those processes. Lots of things could happen. We could lose power. We could get scaled up and scaled down, well, down in this case. Or we could deploy new code and need to restart our production processes. And then we'll lose the state because it's in memory. So that's one thing. So we need some durable place to store the group data. So like the list of messages and the name of the group and the members and stuff. But we also want to be able to have more reliability in a couple other parts. One is calling OpenAI's API. It sometimes goes down. If you haven't used ChatGPT before, there are often times when it's like, something went wrong, try again. It would be nice. So sometimes it's down. We want to be able to retry whenever the API call fails. And it also might be hanging, so we want a timeout. So we want to time out hanging calls and retry them. And we also want to maintain the state of where we are in our business process. So in this case, we have a pretty short business process. Often AI workflows are longer, but we have a few steps to do. When we get a message, a create message mutation from the router. I'm the messages subgraph right now. I need to save it to the database, and then I need to, what it does is wait 10 seconds to see if any other messages come from the other users, and then batch them together and do the OpenAI API call, get the AI response back generated from the LLM, and then publish that message. So it's 3 or 4 steps, and I guess 4. And we don't want to not finish that sequence of steps. So again, if this process dies in any of these steps, then my users won't get the AI message. They'll be left hanging. They'll ask a question and they won't get an answer. And I want to avoid that. So I need to somehow checkpoint state, save where I am in this process so that I can pick it back up in the future if I die. So the common way to do this is you both have the database for storing the state and also a job queue and some worker pool that's pulling on the queue, picking up new work. And also noticing when work gets dropped because the worker process died, so picking up lost work as well. So this is more reliable, much more reliable. We don't lose state when the process dies because it's in the database. We have a queue with stages and that we can make so jobs that we can make sure eventually get to completion. And we can also really easily do retries to the OpenAI or retry webhooks to the router. So when I get a response from OpenAI, I'm the worker. I need to somehow get it to the router, and it's easier to go directly with this webhooks, another nice feature of it. And maybe, I don't know, the network is broken between me and the router. or OpenAI is temporarily down. Both of those, I want to be able to retry, and it's easy to do that like by putting a job on the queue, saying like, retry this again in 1 second, and then 2, or then 4, et cetera. Great, so we're much more reliable, but we've got another problem. This is much more complicated. We've got a queue and a database to maintain. We've got a worker pool to run, and we've got lots of code to write to do the like putting things on the queue and picking it up and saving state and reading state. And it's a lot to code. Even in AI days when you can have it code it for you, there is a lot of code to write and also a lot of code to get right. Like it can be pretty complex code to get right. And by right, I mean like resilient to failure. Like there aren't any edge cases in which like a certain weird type of error state happens and you wind up with inconsistent state. Like one possibility is the messages subgraph gets a new message, like a create message mutation, saves it to the database, and then puts a job on the queue, like a delayed 10-second start the AI thing. The problem with this is that like if something happens between those two steps, like, oh, I can't reach the queue, so I'm retrying, but then my process dies, the message is processed before I write to the queue, then we're in inconsistent state. The database thinks that we've received this message, which means that we always like will have an AI response within 10 plus seconds, but it doesn't happen. We don't have that job, we lost it. So the way to handle this is a transfer queue or a transactional outbox where you write the job atomically to the database on the bottom, along with the update to the group state. And then you have some other process that eventually transfers these mini queues in the same partition as the group state into the big queue, or the main queue on the top. So anyway, this is just one of the many examples of like ways in which you can code this like wrong, or like in a way where you will have inconsistent state or bugs in the future. So it'd be nice if we didn't have to write this code and didn't have to maintain these systems. And you can. You can replace those three things with a durable function. And the way that works is when a user creates a new chat group, they say create group mutation to the messages subgraph, and messages subgraph starts a durable function for that group, like with that group ID. And the durable function runs for the lifetime of this group chat. So if I never delete this group chat, then it's running forever. And it has some cool properties, this long-running forever function. One is that I can send it messages, or I can call RPCs on it. So I send it a join RPC when a member wants to join this chat, and then the function can define a handler to like add the user to the list of users that are members of the group. I can also like have a send message RPC that I can call on this long-running function, and I can also get data out, like get the current state of the group. Some other cool properties of this function are that anytime it calls to the outside world, like hitting the network, in this case, HTTP requests to the OpenAI or a router, those are automatically timed out and retried, and it's sort of seamlessly done for you. You don't need to like code that logic. And it also the process can crash, and your function will continue running like on the same line with all the state intact, local variables, threads, call stack in another process. So first, let's look at how the federated subscriptions works. And we can use Apollo Sandbox to see the operations that are behind the app. So first, what we can do is report user activity. So this is a mutation that winds up getting routed to the user service. And it's done by the client every second or so to say, OK, this person is still online. And it's taking the user from the auth header. Mutation join or create group. So I want to join or create this group. It's already been created. It has these members, and now it has me, because I just joined it. query. I can query for a group. And what happens is that group query gets routed from the Apollo router to the messages subgraph, which does an RPC call to the group function, the group durable function, and says, hey, give me your state, and then it just returns it. And now we can start our subscription for new messages, and they'll appear here on the right when we get them. And I can send a mutation, send that's creating a message, and over here, I say, give me the best joke about GraphQL, and theoretically, if the Wi-Fi works, we should get, yes, a joke from OpenAI. Why did the GraphQL developer break up with Rust? Because they wanted more relationships. All right? Yeah, so that's sort of the structure of the subscriptions. And what happens is that, actually, let's look at the subgraph schemas. We've got, so port 4000 is the Apollo router. 4001 is, I think, the user schema, or no, the messages. User schema. So the user schema is the only one that has the name and online properties and has this mutation and has the reference resolver for the user entity. And then here is the messages subgraph. And we can look at their schema. What do they define? We've got the subscription, message sent, and every time there's an event, it's a message object. And message has a sender, but the messages subgraph doesn't know any user data besides the ID. So when it sends things back, it just says sender and then an object with just an ID in it. So that when that gets back to the router notices, OK, I've got a subscription event. I've got these clients that have requested it. And they, in their subscription operation, when they started it, selected the name and the online fields from message. And I don't have those right now. So I need to get them from the graph. And it does the entity fetch from the user service. Yeah, so that's how the federated subscriptions work. And we can see a little bit of the code. OK, so this is the code for the app. There's a package JSON, so we know we are in JavaScript land. Turbo.json means we're in a turbo repo, so a mono repo with multiple modules. And the modules are inside our workspaces, so inside the apps and packages folders, which are up here. So we've got a few apps. We've got messages, so the subgraph for messages, the subgraph for users, the Apollo router, the web, which is the Next.js application, and worker, which is the thing that runs the durable code. Then we've got some packages where a durable function is, and some type gen and config and UI components. And right now we are looking for subscription code. OK. Inside the messages, we've got some Apollo server with query, mutation, and here's the subscription. So whenever a message is sent, this one isn't using the webhooks. It's just using a WebSocket. So it's using the in-memory pub sub. You return an iterator, and you publish to it whenever you get a send message mutation. Next up, durable functions. Let's look at what that code looks like. So we're here in packages, durable functions, index. And we have this one function called group chat. So again, this is called once when the group is created. It's given the user ID of like the first of the creator. So we start out with a group having a single member, the creator, and no messages. And then we set some RPC handlers. So whenever we receive the get state RPC, we just return the group. So the local variable has the group state. and then we set a handler for whenever a message is sent to us, we receive the message, and we push it on our array of messages, and we add this user to the group. And then we have a join group RPC where we add the user to the group. And then here's like the main logic. Forever, we wait for a message to appear in the array, and unless it's the first one, we're going to wait 10 seconds for more users to send messages, and then we will get the AI response, and then make a message object to then publish so that it goes out on the subscription. And then it goes back up to here and awaits in condition. And while it's waiting here, we might get an RPC from the messages subgraph from a new message mutation that will call this send message RPC and push it onto messages. And then all of the waiting conditions will be reevaluated, including this one, which will become true. And then we'll wait 10 seconds. And then maybe during those 10 seconds, some more messages have come. And so now this get AI response group.messages has a group, more than one to respond to. So some nice things about this are that I can, as I said before, the process could die. Like I'm waiting on this step right now, and there's been a few messages, so I've gone through this loop sometimes before. Process running the function dies. The system will notice this, and so you have a worker pool running that has this code that you deploy, and the execution runtime will bring this function back to this current state in another process, and the group local variable will have all of the messages that were sent to the original invocation of this function. And yeah, everything will be in the same place. So it's nice because you don't have to use the database. You can trust that the data you put in these local variables is effectively durable, automatically. And when you do something to the outside world, like get the AI response or publish the message, these functions are, they feel like you're directly calling them, but they're actually proxies to function definitions and serialized and scheduled and timed out and retried. And that's done durably so that if this process dies, between retries, the next retry will actually happen. Get picked up by another worker and run, and then reported back, and then this will be rehydrated to this place in state of execution, and it'll resolve. So this will happen reliably until this eventually succeeds. So that's the durable function code. And I want to take a step back and talk a little bit about this architecture, which is sort of anytime I'm trying to fetch data, I'm using a federated query or a federated subscription. And anytime I'm changing significant data, then I'm sort of offloading that to a durable function so that it can be reliable. And I think we have time to look at how that's offloaded. The message is basically creating functions and then sending RPCs, basically proxying to the function which does the work. So this is inside apps, messages service, source, index. What are the resolvers? So when I get a group query, so temporal.workflow is sort of the thing that talks to the durable function. You can think of it sort of like a database client. You get a handle to this particular group function, which is you get referenced by the group ID, and you query it, saying I want the get state RPC, and this is like nice and type safe, and you return it. When you're joining or creating a group, you first try to start this durable function, and if that fails because it's already started, then you just send it an RPC, like the join group RPC. And then you return the current state of the group. Send message, similarly, you're getting a handle to that durable function and then sending an RPC to it. So I really like this architecture, sort of reading done by federated GraphQL and writing done by durable functions. And I think it sort of fits what Martin Kleppmann recommends in the Bohr book, the Bible of Distributed Systems. Towards the end of it, he says, like, based on all the stuff that I've taught you earlier in this book and all the problems, systems that you build should have two things. And the first thing is a unified query interface to a wide variety of underlying storage engines and processing methods. This might sound familiar. If you put a subgraph in front of all of your storage engines, then you could federate them in a unified query interface. So I recommend GraphQL Federation for this. And systems should also have, they should synchronize mutations across different services or data stores through an asynchronous event log with idempotent writes. And the reason for this is, like, he goes through all the difficulties of trying to synchronize state updates across multiple places in distributed systems. And he's like, this is the only way that, like, you can reliably get this to work. And so this is often done, async event log with idempotent writes would be like you're doing change data capture from a write database to like read views with CQRS, command query responsibility segregation, or you're doing event sourcing, again, materializing your read views from an event log. And these are a bit involved to like commit to and implement. It's a lot of code and a lot of things to get right or get wrong. And it just so happens that most durable execution systems are implemented under the hood with an async event log with idempotent writes, and are able to give you the benefits that Martin is recommending you use them for. So you get the consistency benefits, the ability to accurately make sure that updates to your state that involve multiple places, like multiple services, multiple data stores, which is very common, happen eventually consistently. And you can do so without the trials of doing like CDC with CQRS or event sourcing. So you get like really nice DX and development speed while still getting the guarantees that you want for reliability. Yeah, so this is like my favorite main point slide of this talk is I highly recommend you architect your application systems with these two things. And a little bit on LLMs. The AI SDK is much more simple than I thought it would be. So we are using Vercel's AI module, getting the generate text method and calling it, choosing the model of Furrow Mini, giving a system prompt. You are a helpful AI in a group chat. You write simple, clear, and concise content. Messages is just a list of objects with the role either assistant or user. And the model knows that like if there are a few messages from the user since the last assistant message, then I will respond to all of the user messages. Yeah, so that's really simple. I am really like I guess optimistic about like how easy it is to get something like so impactful. So that's all of the AI-related code in the whole app. And then v0.dev is what I used for generating the UI for this application. It was really easy to use. Highly recommend it. It generates a React code, including like updating React state and Tailwind classes. It makes it really easy to add to your code base. And then Cursor is the editor I used, sort of like an AI native VS Code. And I was like I'm already like a AI optimist and enthusiast, but I was very surprised by how much time it saved me and how effective it was. So one example would be like I asked the AI inside the chat, inside the editor, can you add a join group mutation and call it when the user clicks the button? And not only did it update the React state, it updated the schema and the resolvers in the messages subgraph. And the implementation of the resolver was correct. And it talked to the durable function, and it added to the durable function the right RPC and state update logic. And all I needed to do was like click apply on each of those code snippets, and it worked. I was very surprised, and it saved a ton of time in building this. Highly recommend you check out Cursor. I was doing it with like with code-based context, so like command enter and O1 preview. I spent $30 on O1 preview for this talk. So that's everything. Looked at the app, different kind of architectures, and how we landed on like an ideal one. Some of how the code looks, and LLM stuff. And I'm at LaurenDSR on Twitter if you'd like to talk or have any questions about this stuff. Check out my book at graphql.guide. It's pretty comprehensive, like almost 900 pages, crazy amount of content in there. Link to the diagrams if you'd like those. And in order to click that link, you need the deck, which is at bit.ly/summit-chat. And I have a huge surprise, which is that we are hiring. I know we're always hiring, but I guess I'll just say that it's the favorite place I've ever worked, and I am impressed by the people I work with, and it's a pleasure working with them. So I encourage you to consider applying, and maybe one day I will see you on Slack. Thanks.